In this video, I'm going to look in detail at a simple mesh editing in SOLIDWORKS and then compare that with simple mesh editing in ANSYS. So you can see the different capabilities that you have in terms of deciding how your model works. By the end of the video, you should really know how to refine that mesh to get the best out of it. So here's SOLIDWORKS, and all I've created in this was in the part file, I've created a thin plate, rectangular plate, 2 meters long and 1 meter wide. Now, if I go to simulation, I'm going to create a new study. Now, unlike what I've been showing you so far, let's do a thermal study and let's make it two-dimensional. Now, the section plane that we want is that one, and the depth, and this is just so we can see the results. I'll make it 1 millimeter. So we just have a thin plate. I'm going to apply a material. I'm going to use, let me see. I'm going to use aluminum. And one of my favorites, 6061 T6. Apply that. And there we go. Now, in terms of a two-dimensional thermal study, the boundary conditions in the equations are very similar to what you've seen in structural analysis. It's just that we call them different things. So the thermal load boundary conditions, in this case, I'm going to pick a temperature boundary, and I'm going to set it to be 0 degrees. I don't want Kelvin, I want Celsius. And I'll put it here. And I'm going to put I'm going to put a heat flux boundary on this side. And I'm going to make it -50 watts per meter squared. Now, here we get to the meshing. Right click, and I can create a mesh. Now, the mesh parameters that I'm looking at, I'd like to have it a fairly coarse mesh because really this is a really boring problem. And I'm going to make my maximum mesh size a whole meter. And I'm going to make my minimum mesh size half a meter. And let's see if it can do that. Doesn't like it, but it did it. And so it created these great big triangles for me. Now, in terms of my ability to change them, I could make them smaller, but I can't really do any more than that. If I run the study, then you can see that I've got a temperature gradient which starts out warm, 0 degrees here, and it's getting colder on this side. If I look at my temperature in Kelvin, it's a fairly small temperature change, but it's an aluminum plate. Aluminum has a very high conductivity. Now, if I go and change the mesh, and I make the smallest size, well, and I use a blended curvature mesh, so went back to that size. And I'm going to use 500 millimeters for both. And now it creates this quite different mesh for me. And let's see if the results look the same. You saw how boring they were in the previous version. Now with this mesh, what's all this? That's an interesting change. And if you don't question the meshing, then you might think that that's really something going on. And yet this is purely a constant temperature here and a constant heat loss here. So we should not see any kind of strange feature like that. This is a purely two-dimensional problem, nothing interesting. In the case of what's assumed in this, this is assumed as a thermal boundary layer, basically fully insulated here and fully insulated here. Now I could go in and I could set up another thermal load. I could put another temperature boundary there and also make that 0 Celsius. Hey kids, what about the assignment? And run the study. And you can see again that because of the strange mesh that I've created, that my results have something to do with the curious behavior of the mesh. I can look at the mesh quality plot in this, and it's showing me that these mesh points here, according to whatever scale they have, are a bit sharper and pointier than some of the other ones. Is that useful for us? Well, it's hard to know. The interesting thing about this is that it's not very easy for us to actually make changes to that mesh. We can go and we can apply some mesh control tools. These enable us to change certain features of the mesh geometry, but we're not really allowed to go in and move points around or slide edges of the finite elements around in this tool. Let's try making
there's
the
an
same
assignment.
steady-state
Keep watching.
thermal model, two-dimensional, using ANSYS Workbench, and see how it differs in the way we can manipulate the grid and the way the solution progresses. Here we are in ANSYS Workbench, and looking down the choices, we could pick steady state thermal right there. And if we just highlight that and drag it into the work area.
Okay, that assignment I keep telling you about, it's gonna be awesome.
Model, and we can just open up the materials, and I'd like to use aluminum, and we don't have aluminum as the default. So if I click engineering data sources, and you'll see that there's a bunch of materials here. If I pick the general materials database, then that opens up a whole lot of other options for me. And I'm actually going to add aluminum alloy to my available materials for this model. But I'd also like to compare with copper, and I'm going to add copper alloy. And once I'm done, if I just close those, I've added those different data sources, those different types of materials to the potential model. Now for geometry, rather than importing the model from SOLIDWORKS, I'm going to make a new space claim geometry. Now, one of the problems with using ANSYS is that, frankly, the different tools are in different modules, and they're kind of annoying that they are different. Now, this one comes up in looking at the XZ plane, in my case, as the default, which for a two-dimensional model, it's not going to like that. So I'm actually going to view it from this view, and I'm going to select this as the new sketch plane. And I'm going to pick the center point with a rectangle, I'm going to pick that sketch plane, and I'm going to pick the center point here as a rectangle. And because I'm going to make this several meters, I'll just make that rectangle. And similar to what you do in SolidWorks, if I pick dimension, I can select from here to there, and that's going to be 2000 millimeters. Sorry, double click that, 2000. And I'm still using dimension. I'm going to pick from there to there. And I want that to be, oh, going to click that tool again, 1000 millimeters. And you'll find that it's frustratingly different in this tool than SolidWorks, but I can change from spin to pan, and pan lets me bring that into the center.
Okay, so here's the assignment. What you gotta do is you gotta...
And so I'm finished editing that sketch, and now it's created a 2D planar component. Now, if I right-click on that, and I check the properties of that geometry, because I want to do a two-dimensional model here, and I'll just drag that up to where we can both see it. I want to make this analysis type two-dimensional there. And so now the model knows from the geometry that it's a two-dimensional model. In order for the two-dimensional to work, annoyingly, it has to be two-dimensional on the XY plane, not the XZ or YZ plane. So be careful of that. So the check marks up here show that we've got our engineering data and our geometry right. Now we can right-click here, and we can edit the model, and this will open up a new window of ANSYS Mechanical. And it's painfully slow, at least on my computer. And this is, again, one of the reasons why you'll be frustrated working with ANSYS if you're just trying to do something quick. But keep in mind that the potential that you have to work with here is quite a bit more sophisticated. Now, it takes a while to open up each of these workspaces. You can leave them open, so that is a possibility once you're modifying things. So our geometry, that's set. Our materials, now we have, if you click materials here, you'll see that we have several material choices that came in from the database. Now, what we don't know is which one of these materials we are working with. And so before you can do the model, we need to assign the material. And I'm going to select the aluminum alloy. Oops, I guess I'm not going to select the aluminum alloy. I'm going to go to material assignment. And now if you look down in the bottom left here, you'll see that it's looking for these yellow boxes to be filled. If I pick the whole body and select that, then that geometry selection, if I click apply now, it knows that that body is the material that I chose, aluminum. And you can see it's got the material assignment showing here. Just for fun, I could let that name show up there, and that should be fine. The next thing is the meshing. So in terms of the mesh, we can look at the mesh, and the defaults for the mesh are shown. I want to make my default, because I'd like to show maneuvering the mesh and changing the dimensions. I want to make the default size of the mesh a meter. Now that's huge.
Okay, so for that assignment, here's the deal. You're going to first use ANSYS to make
there. So it created a mesh, and when I'm in the mesh tool, this circle target shows the approximate size of my mesh elements. Now that's a pretty sparse mesh that I've got, but that doesn't stop me from solving it. I can now go and look at the steady state thermal. So I want to set a temperature boundary condition on this side. And when that was not what I wanted to pick. What I wanted to pick was an edge. So you can look up at these selection tools. I want to pick the edge, and that's the edge that I'm choosing. I apply that geometry, and you see over here it shows that I'm applying one edge, and I'll make that 0 degrees C. And so you see that the temperature is showing up as 0 as that tag, and you can see that boundary condition. Now I'm going to put in another boundary condition. This will be a heat flux. And for this, I'm still in selecting the edge, so I'm going to pick that edge. I apply, and you can see that I've got that edge chosen. And I'm going to make this 100. And that's in watts per meter squared. So it's an assumed thickness in this case. And then beyond that, I can look at perfectly insulated. Once again, picking an edge, and I want that to be perfectly insulated. Apply, and it's that edge. And I'm also going to pick perfectly insulated for this point. Apply that. And that's done. Now I can just I can see the mesh, and I can solve this.
You're going to use ANSYS to make a CAD model of a round plate.
Now, if you look at the solution, nothing really has changed, except we haven't really chosen to see what we want reported. So I want to report the temperature, and I want to report the directional heat flux. That'll be interesting. And I can solve that. Now, if I look at the temperature, there's my temperature map, and you can see how coarse that is. But notice that because my grid is so simple, the gradations the contours are simple too. I can choose smooth contours, and it looks like so. You can also mess around, unlike you can in SolidWorks, with the color scales, and all you have to do is grab one of the bars, and you can adjust the color scale so that you can highlight different parts of your model. Now, going back to the mesh, since the purpose of this demo was to talk about modifying the mesh, I'm just going to go here, and you can see that I can add a mesh edit function in here. So if I just click mesh edit, this new tool comes up, and I'm going to choose node move. So there you can see I can select a node and move it. I can select another node and move it. So I can make these elements really whatever suits my problem. Now I can't choose the elements here because, of course, they're on the boundaries, so they're moving those would be a problem. So with that modified mesh, Now I can go and solve again.
Now the round plate has to be insulated on the outer side, and it has to have heat generation on the inside at the center.
Edge select. That edge.
It's going to be 1 meter in diameter.
Apply. And I don't want it to be 22 degrees. Maybe I want that to be 10 degrees.
It's going to be 1 centimeter thick.
So now you can see I've got my boundary conditions showing up here in, if you click solid state thermal, I've got a heat flux of 100 watts per meter squared at A. I've got a heat flow that's insulated of 0 watts at B. I've got a temperature at C of 10 degrees C and a temperature at D of 0. And if we look at my mesh, I've got this wonky mesh that I created. So let's try solving.
It's going to be made of aluminum.
Now you can see my temperature has changed, and because this mesh is so coarse, I've got a rather wonky temperature distribution, and my heat flux definitely looks a little crazy. And again, you can modify how that graph looks just by simply dragging up and down the color bars.
And then you're going to figure out it's...
So that's a really simple version. Let's try and I'm going to delete the node move that I did.
Oh, it's time to heat up. How long will it take to heat up?
I'm actually going to modify this mesh. Our default element size, let's make that 0.1 meters. And let's update this. Now we've got a mesh that's a lot more realistic looking. We can still go into mesh edit, and we can still look at moving nodes. And I can move any particular node around, and I can modify that two-dimensional mesh.
What's the heat source?
And when I'm happy with it, click solve.
It's internal generation.
And now we look at the temperature distribution, and you can see that now this is looking a lot more involved and intricate. And perhaps I want to make more of the blue and less of the red. And you can modify those color contours to get something that you like. We can do ISO lines instead of the smooth contours, or color bands. All of those things you'll play around with to get the graph to look right. Now, the fact that we can look at moving individual nodes and making the mesh suited to whatever geometry we have is tremendously powerful. And we'll look at ways to use that in the next video.